Alright, upon getting the calculations for the first bridge, we were able to dive into the second bridge, which is the thick straw bridge. Now, to our surprise, after performing the tensile test, it was actually determined that the second bridge and the first bridge actually did hold the same amount of maximum loads, which was 0.28 kilograms. Even though that the second bridge did weigh a little bit more, it did ultimately hold up holding the same amount of maximum load, which was 0.28 kilograms. And with that, we're able to drop our free body diagram that you see on the left with the load of 0.28 kilograms down the middle. And with that, we're able to dive into the calculations and more or less get the numbers. So yeah, so with this one, we also did where we got households of appliances, the same as the first bridge, and we would weigh them before and place them in the same spots as we were for both bridges and recording the results up until it couldn't hold or sustain the weight no more. And with that, we got to 0.28 kilograms. And with that, we're able to dive into it. So we start off by going into the reactional forces. Now, we are going to assume that the reactional forces are the same due to the fact that we're going to assume that the bridge is perfectly constructed and evenly distributed. So R1 and R2 will be the same as far as the reactional forces. Now, we start off by getting the mass of the second bridge, which is 0.235 kilograms, plus the amount of weight it was able to hold, which is 0.28 kilograms. And we add that together, and we are going to multiply that times the unit of gravity acceleration, which is 9.81, and with that we get 5.05215. Once we get the 5.05215n, we're going to divide that by 2 due to the two reactional forces being equally distributed. So since R1 and R2 are equally distributed, we're going to divide the 5.05215 by 2, and with that we get 2.526n, and that is going to be our reactional forces for R1 and R2, 2.526n. So that is our reactional forces. And then with that, we're able to dive into the maximum bending moment. So again, we're going to get our total weight, which is 0.515, divided by the length, and that is going to give us our 1.931, which we need for the maximum bending equation. And with that, we get 1.931. And we plug that into the equation times the length to the second power divided by 8. And with that, we get 0.0171 kilograms mass. And that is going to be our maximum bending moment. And with that, we go on to our final one, which is the shear stress. Now with that, we have to find the moment of inertia for the truss bridges. With that, we plug into our steps by getting height to the third power minus inertia to the third power. So we start off by getting the height to the second power meters minus the length to the second power meters, and with that we get 0.08885. And with that, we're finally able to plug it into the equation of 0.0171 and times 0.0335 and divided by 0.08885, and with that we get 6.4 pascals as the maximum shear stress. So the reactional forces was 2.526n. The bending maximum moment was 0.0171 kilograms mass, and the shear stress was 6.4 pascals. Thank you so much.